Last time we looked at this simple problem of a 2 mass and 3 springs. One of our biggest difficulties when we are doing this is to determine what is the direction in which the object is moving. And apart from the direction, how do we determine whether it's x1, x2 and so on when we are looking at and what's the direction of forces acting? For example, we looked at the Newtonian method. We said the spring 1, the force is this way, spring 3 is this way, and the difficult part always often comes in, what is the direction of force in which the force of the spring 2 is acting? This is one of the difficulties that most often the students face when you're looking at the Newtonian method. So let's try to see how to solve the same problem using the Euler-Lagrange equation or the Lagrange method, right? So let's try to solve the same problem with the Lagrange method. So let me just rewrite that problem here just so that we can recap. So we have spring 1, we have a mass 1, and we have a spring 2, we have a mass 2, so K2 and M2, and we have a spring 3 with spring constant K3. Now we said that we assume that M1 is moving in this direction, which is x1, M2 is moving in this direction, x2. So if we have two objects, then the relative motion of the two objects is, let's say, how much is the body 1 moved minus how much the body 2 has moved. Now since the positive direction is in the right direction, so the body 2 moves in the left direction, and it's essentially negative, minus x2. Right? So if I do x1 minus x2, so then automatically that would get added up in there, right? So that gives us some idea of what is the relative motion between the two bodies, right? So what is the relative distance between M1 and M2? So we assume that when we assume mass 1, okay, they seem to have changed the interface of this app somehow. M1 has moved by a distance of x1, and mass M2 has moved by a distance of x2. Then the relative distance, let me call it relative distance, is nothing but x1 minus x2, right? So now if that is the relative distance between these, then that is the compression or extension of the spring K2. So we are not worried about what direction, if it's compressed or if it's extended, right? So if x1 is larger and x2 is smaller, then the spring is going to get compressed. If x1 is larger, smaller than x2, the spring is going to get elongated. We know that. Doesn't matter what the distance is, x1 minus x2 gives us the relative distance between the two objects. That gives the amount of either extension or compression in the spring. Now we are not going to bother whether it's extension or compression. That is something that we don't care about. We are writing the energy, right? So our goal, let's recall our Lagrange equation. Recall Euler-Lagrange equation. So let's say in conservative form. So why are we using conservative form? Because we assume, one, that the surface is frictionless. Second thing, we assume there's no dissipation. Then we don't have any damping. So automatically there's no dissipative effects. There are no external forces acting here. That means the whole system is conservative, right? So we could then write our Euler-Lagrange equation as d by dt of dou L by dou. Let's say I will write as qi dot minus dou L by dou qi. So qi is nothing but our generalized coordinate, which is nothing but our x1 and x2, right? So we have two equations on x1 and x2, so we can write it. So what is L? L is nothing but our T minus U. T is nothing but our kinetic energy, and U is nothing but our potential energy. Okay, so let's try to write the kinetic energy and potential energy of the system. So we have two masses, m1 and m2. So m1 is moving at x1 dot square. Similarly, half m2 into x2 dot square. We'll try to explain that. So we have two of these masses. m1 is moving at some x1. It is moved by some distance x1, but it's also moving at some velocity. Velocity of this m1 is rate of change of the distance, right, or rate of change of position. So d by dt of x1. How fast is the position changing? Similarly for m2, how fast is the position changing? D by dt of x2, which is what I am writing as x2 dot. So this is nothing but square of dx1 by dt whole square. Similarly, nothing but dx2 by dt whole square. Right? So I can easily write this as my kinetic energy. Similarly, I can write my potential energy is coming from three springs. Right? So that's half k1 x1 square, that is the elongation of the x1, the spring k1, because the mass m1 has moved, plus, I'm just going to leave this here, half k3 into x2 square, that is because the mass m2 has moved by x2, so it's compressed, it's moved the spring k3, either it's compression or extension. We'll not worry about that now. We are not worried about the distance. If x2 is positive or negative, the square term is always going to be positive, right? So it's the energy we are worried about. Similarly, half k2 into x1 minus x2 square. So we talked already about that the x1 minus x2 is the relative distance, right? So we are not worried about what direction it is moving. The relative distance between the two masses is x1 minus x2. You can use x2 minus x1 like we already saw last time. You can use the opposite and you will still get the same equation of motion, right? So now we can write the different terms in our Euler-Lagrange equation for mass m1 and m2. Let's try to write this side by side. So let's go back a bit and try to write the Euler terms related to our Euler-Lagrange equations for the two masses, right? So let's try to write each of these terms and we'll try to see how to get the final solution for the equation of motion. So dou L by dou x1 dot. Similarly, I need dou L by dou x2 dot. x1 and x2 dots are essentially the velocity terms, and all these terms are only available in the kinetic energy. The velocity is only available in the kinetic energy terms, right? So I can easily write this is probably most simple one, m1 x1 dot and m2 x2 dot. Similarly, I can write the time derivative of this is nothing but m1 x1 double dot is m2 x2 double dot. And the second term that we have is dou L by dou x1 and dou L by dou x2. x1 and x2, the position terms are only available in the potential energy. They're not there in the kinetic energy. But one thing to be very careful about is that our Lagrangian is t minus u. So you have the negative sign that you need to be mindful about when you are doing it. So there's a minus sign here, just to be mindful about it. So I also make that mistake often, that I miss that minus sign, but just something to be mindful about, otherwise the signs will change there. Right? So if I take the dou x1 term, then I have minus k1 into x1, which I am getting from this particular term here, term 1. Then I have, similarly, I have the minus sign because I have the t minus u there, right? So because of the t minus u, I get a negative sign here. Otherwise, I would have a positive sign there. Okay, so my God, this interface is becoming a bit tricky to do that, right? So maybe I think okay, yeah. So that's a nice thing. So because I have because of the negative sign here, I get this negative sign here as well. Okay, so now let's going back to it, and I have what are the other terms which relate to x1 is minus k2 into x1 minus x2, right? And similarly for the x2, if I take the derivative with regard to x2, I have one x2 term coming here. Oops. Can do a line. I have one x2 term coming here and one x2 term coming here, right? So if I would go back there and try to write these things down, I would say then I have there's a minus k2 into x1 minus x2 into minus 1, because I have the negative sign here in front of x2, minus k3 into x2, or I can just, I'll rewrite this, I'll use all the, remove all the negative signs in there, so just so that we are, so I'll remove this negative sign and the minus 1 here, so I can say k2 into x minus k3 into x2. So let me try to collate all these terms. If I try to bring all of them back here, so then I can write my equation of motion for mass m1 is m1 x1 double dot, there's a minus, so plus k1 into x1 plus k2 into x1 minus x2 equal to 0. Similarly, here I have m2 x2 double dot minus k2 into x1 minus x2 plus k3 into x2 equal to 0. Or I can just simplify, I can rewrite this as x1 double dot plus x1 into k1 plus k2 minus x2 into k2 equal to 0. Similarly, m2 x2 double dot minus x1 into k1 plus x2 into k2 plus k3 equal to 0. So this is our equation of motion obtained from the Euler-Lagrange equation. Just to compare, I also copied the equation of motion that we have obtained from the Newtonian equation. As you can see, there's a we are getting the same equation. Okay, maybe I made a mistake, so this should be k2. We are getting the same equations. It doesn't matter what method you are using. So the advantage that we had with the using the Euler-Lagrange equation was we did not have to determine what directions are these forces acting, right? That made things very simple when we were trying to write our equation of motion. All we needed to worry about was what is the term related to each of these extensions and the energy terms, right? Okay, thank you very much.